Campo is going to finish his lecture today. Okay, because we can delay so he has for 10 minutes or 20 minutes, but we understand that.
10 minutes, 10 official. Sorry? 10 official minutes.
I think officially you have 10, but I mean we are going for 5 minutes with 20.
Yeah, it's easy. I divide every minute in 3.
Do you know about roughly how many minutes I went?
Okay.
20 minutes.
How many?
20 somewhere around.
Yeah, tank here.
Sorry?
Tank flying.
Okay, you need to write it. No.
Even you.
Continue there. So, you understand when I cut the surface along those curves, I get a polygon. Breaks open. To see that you have a polygon, do the following experiment. Take the point on this surface and take some other point at a complicated place and figure out that whenever point can go to every other point without crossing the cutting lines. That means that the picture you get here is connected. This experiment you have to do yourself. I don't do it for you because that will destroy this picture with more curves. So then here we have this one form. And we have the map. You have this is a piece of the plane, and this is the map from this to the surface. The easiest model is the case of an interval. If I have an interval and I wish to make a circle, I need a map from the interval to the circle. So the usual map is t goes to e to the power 2πit. That runs then around the circle once. And this sends the beginning point of my interval to the end point of the interval. This interval is the interval 0, 1. And here we have exactly the same story. That when I cut along those things, instead of getting a one-dimensional interval, I get the surface. And again, the polygon. And to get the surface back, I must remember which one corresponds to which one. So when I do this, when I approach this, that means I approach the cutting line, and then I approach the cutting line from the other side and you loop like this. So we have our one form, and this projection map is an exponential here, I call it E. It's a kind of general formula. E from exponential, but it's not an exponential. So what I can do is I can give back the differential from alpha to this surface. And this form I can write it as d of a function. Ramon told us if you have a star-shaped region, then every enclosed one form is d of a function.
Can I just propose something? We make 20 minutes official and don't rush.
I was rushing.
No, but I feel that maybe you are allowed to.
Okay. Okay. So no, when we do this, then I have this function on the polygon, but I need the function here. So better the function. If at this point when we identify this, I need that the function has the same value here as here. But the difference of value of those functions of this capital F function is the path that they run along this curve, which is one of the obstructions. I forgot where they are in this record. They are here. It's one of those obstructions. So, with this obstruction vanishes, then at least the function will be here and here. But then it is the same one form here and here. So if it agrees there, it will agree also at here right form. So it will agree along this edge. And if all obstructions vanish, I can go back and get a function here. So I have proved that if all those integrals are 0, then the form alpha is exact. Now I must make enough, I must show that those obstructions are independent. So what I do is, if I need to show that this obstruction is independent from the other, I look for an example where this obstruction is present and all others are 0. So I take on the polygon function which is 0 here, which is 1 here. That means that the path integral is measuring the difference between 0 and 1. So that means 1 of my integrals is 1. And then I extend this function by drawing the levels. Then I have a function, I have a one form, d of this function, which is closed because the d of the function, but cannot be exact because there's one of the obstruction and all the others are obstruction are 0. So if you can do this, it means the obstructions are linear independent. So that means the space of this space is exactly of this dimension. So we compute the rough convolution. So what I wish to do next is finally go to Riemann surfaces. And for this I need one extra kind of field.
Did you assume orientability so far? Or do we
It was on the surface of genus G.
Yes.
And I put genus. This surface first had 3 mobility. 1 and 3 was orientation. If there's no orientation, so it changes slightly. Not completely wrong, but changes slightly. So we need more fields. So a field, now you know what it is. Field is a map. U again. U is such that in a vector space. And now this vector space is in fact R2. So it's a 2-dimensional real vector space. I write it like V, but I wish that nobody sees the basis. So what is the J field? The J field attaches to every point in that open subset of V, something related to V. And I combine both ideas. First, I write something which, if you don't understand, it's not a problem. So we have already a field. As an example, we have numbers. We had V. This was vector field. We had V star was one form. And now we wish something else. It is the endomorphism of V. So I attach to every point an endomorphism of V. An endomorphism of V is a linear map from V to V. So an element here is G index P, element here. G index P itself is a linear map from V to V. That's the J field. Not exactly. I ask properties of this J field. A J field is such a map. So the J field is a map with properties. The number of properties is in fact very short, only one property. I wish that at every point, that if I compose JP with itself, that this is the identity of this minus identity of the vector space V. So JP is a matrix. Because it is an endomorphism. If I choose a basis which is hidden in this notation, then JP becomes a matrix, and I ask that this matrix, as the morpholess property multiplied by itself, is minus identity matrix. So at every point, you give yourself 4 numbers A, B, C, you think them as a matrix, and you ask that this morpholess thing happens. So a Riemann surface is a surface And if I say surface S, we ask the three properties, orientation and so on. Is the surface S with a J field. So now J field is slightly more complicated on the surface. The surface you should think is covered by open sets. In each open set we have such a J field, and there where the covers coincide, the J fields coincide. That's the Riemann surface. You can ask, does it exist or not exist? What I wish to do now is to make examples of Riemann surfaces. And then tomorrow we show every Riemann surface is like an example we made today. Today we will make beautiful Riemann surfaces, the examples which we can give concretely, and the statement every Riemann surface is like that and is like that means we can uniformize Riemann surfaces. We have in our head a stock of examples, and then the theorem is, uniformization theorem is, every Riemann surface is in our head. So I must make Riemann surfaces. So the way of doing this is, I must remember how to make torus. So let's imagine we wish to make this torus. So how we do? We take a two-dimensional vector space. So for me a vector space is only one thing which needs to be stressed, it's the origin. So here is my vector space. And then I wish to make a torus. So what I do is I choose two vectors, u and v. Those two vectors make a parallelogram. And then I use v to identify this edge to this edge. And I use u to identify this edge to this edge. What I say at this point, I add to it v. That makes this point, so those 2 points get identified, and do the same with this point and this point by translation by u, and I get such a torus. But I wish to have a J field. To have a J field, I think that this plane is the plane of complex numbers. The best name is called the Gaussian plane. The Gaussian plane. The Gaussian plane is the set of all numbers a plus bi, where a and b are real numbers. So, of course, now the picture changes. The picture changes drastically. Because it seems there are more elements which have special nature which I can draw. So we start over again. So we draw this vector space which only the origin. But we certainly remember this vector space was the Gaussian plane. So somewhere it's a guy which is 1. What we do is, let's by convention say our first vector is this vector. We must change 2 vectors. So what I can do, I can rotate this picture and I can dilate it as much as I wish. So I can rotate and dilate in such a way that this vector is just the vector 1. Then the vector v is somewhere. But we wish that now we wish to have an oriented surface. And what we wish is that the 2 vectors u and j of pu, we wish that they agree with the orientation. So if the orientation is the orientation of the blackboard, and the orientation of the blackboard is this convention, watches to the left, then if this is the vector u, j of u must be here. In this picture, that means j of u is above the real line. So, this vector v must be somewhere above. many tori with J field. Let's see if we see this J field. First, when I take, so I say many tori, it only depends on this V. Topologically, it is, I take the parallelogram made by 1 and V and divide by our rule. Then I have the topological space that makes the torus. But if I take a point, this point sits in the Gaussian plane. And in the Gaussian plane, if you have some point somewhere and you have a vector, you know what it means, turn by 90 degrees, multiply by I. So I take as J field multiplication by I. So now we see, if I wish to have an overview of all tori that are surface of genus 1, it is just enough to choose one vector in this piece of the Gaussian plane. This piece of the Gaussian plane is called upper half space. And H was used too much, I prefer this notation. C plus is upper half space. So every point in C plus gives me a torus with J field. One of the theorems is already all Riemann surfaces of genus 1 can be made like this. So for every such surface, there is some vector in the upper half plane, which makes my torus. So this gives a construction of it. The idea is now to do this in every genus. And therefore, I need to understand the upper half plane much better. So I need now 6 minutes. Still possible?
6?
6.
And only 6 minutes?
Yeah.
And only 6?
We can agree.
I hope so.
You just used 30 seconds, so get going.
How many seconds?
No, 5.5.
5.5. I wish that we discover a geometry in the upper half. And what is the geometry? The geometry is something such that we have special subsets of our set. So, geometry in the plane starts out as each time we have 2 different points, there's exactly one line through those 2 points. And those lines at the end satisfy a lot of properties. So a geometry is, you have first a set, and then you must make a list of subsets such that nice things happen. So first thing, I wish to make a set. So I take the ring of all polynomials in one unknown, I do not say that, in one unknown with real coefficients. That is something everybody knows how to work with this. You write out the polynomial, you can add and multiply. But this thing has a big disadvantage. It's not a field. So what I do is, I consider the set of all surjective maps to a field. But this is the field in the sense that we can add and multiply. It's not a field like agricultural field, the field, every point something. So I take the set of all such surjective maps, but the map itself has the quality of being a ring map. To be a ring map means sense addition to addition, multiplication to multiplication, and then 1 to 1. So I take the set of all ring homomorphism from this ring to this ring. And this set breaks naturally in 2 pieces. Piece 1 is the affine real line and it is disjoint union in another piece, which is the hyperbolic plane. Hyperbolic plane is a plane that competes with the Euclidean plane and has also those lines, and those lines satisfy properties, but they miss property number 5 of the Euclidean plane. If you have a line and a point, then there are many lines through that point that do not intersect your line. So the fifth postulate is wrong. And this is extremely easy to see. How many minutes is this?
3 minutes.
Yeah? What?
What did you ask? How many?
How many minutes?
3.
Or still 3. So then we must see how do we make such ring homomorphism. So a surjective map to a field is surjective map of a ring, this ring, to a field. I do not know nothing about this field, but if I wish to understand this map, it only depends on the kernel. This map, phi has a kernel. So phi is determined by its kernel. That's for those elements in the ring which go to 0. And this must be an ideal, and this must be a special idea, it must be a maximal idea. But this ring has as maximal ideas only ideals of the following type. We have ideals of type x minus a. A is a real number. Those correspond to surjective maps where the field in question is the field of real numbers. And then we have ideals which are generated by things where b is also a real number, by things of this type. Well, when I put round brackets around the polynomial, that means I take all multiples of that polynomial, which is an idea. So these are those polynomials which have the property no real roots. And the school below this has something to do with the inequality concerning B and C. So we have two kinds of points. This kind of points gives this affine part, and this kind of points gives this hyperbolic part. But we did not see the lines. So the lines, they appear as follows.
1 minute, please.
Yes, it's enough. The lines appear as follows. Now, if you have such a polynomial without roots, then I can, in a complex plane, I know it has two complex roots. So I write z, b, c, that is the root of that polynomial, which is a Löcher-Hoff plane. And we forget the other root. So this point is enough, is a good notation for that polynomial. Now I take two such polynomials. And another one. And I combine them in a convex plane. I do t times the first plus 1 minus t times the second. Then the root of this polynomial will travel. So now I get a point which depends on t. The model thing which everybody should do when to high school is, so I have two polynomials, I would have another point here, z, b prime, c prime. And when I do this construction and let t vary, then the root varies along the circle, which is perpendicular to the boundary, which are exactly the hyperbolic lines of the plane. I think this is the easiest introduction to hyperbolic plane.